All right, good afternoon. If you've already started working on the Chapter 2 homework part, not necessarily the learn start part, but the homework part that requires the Chem plugin, a couple people have told me they've had a little bit of problems that their computer doesn't think it's been installed. I'm not sure if that's true or not, whether if the first installation, if you did it before, has issues and you need to reinstall. But if you do have problems, let me know. Try to install it, restart your computer. I would say the advice I've been given is that you should maybe use Firefox as your browser to access that, as opposed to Internet Explorer or and I know on the Mac, Safari sometimes has some issues. Safari won't work with the Chem plugin, but Firefox does work. So try Firefox, and if you do have problems and you've tried that over the weekend to see if the Chem plugin works, let me know. Maybe I can help you out. Maybe not. If there are serious problems, I'll let McGraw-Hill know, and hopefully they can fix them. Okay, I want to continue talking about alkanes and cycloalkanes. Structures, properties. We talked about the fact that alkanes, we can have all kinds of different configurations of these alkanes depending on how we connect that chemical, the carbon backbone for alkanes. So they can be just connected all in a single chain, what we refer to as a linear alkane, or those carbons could be branched. Once you get enough carbons, you could have branching, such as the case once you get to 4 carbons or above. So we have in the C4H10 butane, there are 2 possible isomers. They could be connected in a linear fashion, or one of the carbons could be branched off of the middle carbon. They have the exact same molecular formula, the same numbers of carbons and hydrogens, but they're connected differently. That's what we refer to as a constitutional isomer. Okay, they're different molecules. They have different physical properties. As we'll see as we go along, there's much more in terms of different physical properties than just the boiling points. Okay, obviously, the more carbons you have present in your molecule, the larger numbers of possibilities of connecting those carbons differently, right? So the number of possible isomers that would be available at a particular molecular formula increases exponentially as you increase the number of carbons. If you just look at butane or pentane, C4 or C5, there's only a few different isomers available. There are common names for those isomers, but once molecules get to be more complicated, we have to have a systematic way of naming them. So if you recall, we talked about the naming system developed by the International Union of Pure and Applied Chemistry. That's very systematic, that allows us to name any organic molecule based on some rules. So if you take this example that we talked about last class, we look for the longest chain. That's the first step in this process. Find the longest continuous chain of carbons that has the most branching. Okay? It's possible that you could number this with the exact same number, for example, this way. There's no difference between this group and this group, so it wouldn't really matter which one you chose to look at. It would be identical. Once you find the longest carbon chain, that's your parent name of the molecule. In this case, 8 carbons with the suffix ane for alkane. So that's octane. Then we identify the substituents or the branches off of that carbon chain. So here we have 2 positions which have 1 carbon. Those would be referred to as methyl groups. And in this position, we have a 2-carbon chain branching off. That's an ethyl group. All right. Once we identify what the substituents are, then we number the chain, that longest parent chain, from the end nearest a branch. Okay? And that's sequential. So if you start from where I've numbered 1 here, you find that there's a branch 3 carbons in. If you start on here, if you start numbering 1 here, you find there's a branch 3 carbons in. No difference. So then you go to the next closest branch, and that would be numbering from the left side. Okay? Because we have a branch on the 4 carbon. If you were to number the molecule this way, that branch wouldn't be until the 5th carbon. Make sense? Everybody on board with that? Okay, then we just put the name together with the locants or the numbers for the positions. So on the number 6 carbon is an ethyl group, 6-ethyl, and there are 2 methyl groups, dimethyl. So 3,4 dimethyl octane, and we put that all together. All right? Pretty straightforward, right? Okay, let's take a look at some other examples. Let's see, let's just draw something here. Okay, how about something like this? Can you identify the longest chain here? 7. So there's a number of possibilities, right? It's 8. So if you start from, let's just start here. 1, 2, 3, 4, 5, 6, 7, 8. That's an 8-carbon chain, right? We could start from here. 1, 2, 3, 4, 5, 6, 7, 8. Okay, starting from this position or starting from that position? Which one should you choose? Is there a difference? Yeah, in this case, unlike the previous example, in this case, those both have the same length of the longest chain, but this one is the more branched. Okay, so this group is more branched than that group. So you always choose your longest chain as the most branched one. Okay, let me see if I can get rid of some of this garbage on here. So we've identified our longest chain. Uh-oh, what did I do? I deleted something. It was like that, right? Okay, good. Now we have to identify the substituents. So if we're starting, this is the longest chain. I'll identify it here. Okay, now we have substituents. So here's a substituent, here's a substituent, here's a substituent, and here's a substituent. We have a couple that are 2 carbons and a couple that are 1 carbon. So again, we have methyl groups and ethyl groups. So we have dimethyl and diethyl. All right. Hopefully, it's very obvious at which point we number this, right? We start numbering from this carbon because it's the closest branch would be on carbon number 2 here. So 8 carbons, put that all together, then our name would have a parent of octane, okay, octane, and then we have substituents. So we have 2 ethyls and 2 methyls, and alphabetically, which comes first? Ethyl, good, you know your alphabet. So we have a diethyl, and we have a dimethyl. And I'm going to run out of room here, sorry. And then we have to put in the numbers. So the ethyl groups are on carbons 3 and 5. So this is 3, 5 dash diethyl. And I should have left myself some room here. And the methyls are on 2 and 4. Dimethyl. That should go in here. Okay? So that's the name of the molecule, this unique molecule of the many, many molecules which have the same molecular formula. And so we can identify directly that structure. So you should be able to go through this process of looking at the structure, identifying the longest chain, figuring out what the substituents are, figuring out which direction you number them, and writing that name out correctly. You should also be able to do the opposite. If I were to give you the name, you should be able to draw the structure of that. That's probably a little easier, right? Hopefully. Okay. Well, you notice that those substituents on that molecule I refer to as methyls and ethyls. As we talked about last time briefly, when we name carbon alkyl substituents, we basically take what the number of carbons it would be for the chain length, according to those names, methane, ethane, propane, butane, and change the ANE ending to a YL ending. So we refer to those as alkyl groups or alkyl substituents on a larger molecule. And we talked a little bit about these examples of some ways in which that kind of naming idea of an alkyl group as a substituent is used in some common naming systems. And I want to talk a little bit more about this. So you'll see some interesting names here. For example, these molecules here on the bottom. They're all isomers of butane, but have a chlorine on it. And 1-chlorobutane, 2-chlorobutane, 1-chloro-2-methylpropane. That's the third molecule, and 2-chloro-2-methylpropane. Those are the official IUPAC names for those molecules. And by the way, if you only remember the IUPAC naming in this class, you should be fine. I won't ask you to remember common names. However, if I happen to use them, I hope you'll recognize some of the common names that we do use. But the IUPAC name you should be able to use. But you'll notice here, N-butyl chloride is a common name for this. 1-chlorobutane. N-butyl chloride. Normal butyl considered like a substituent. Okay. This one, sec-butyl chloride for 2-chlorobutane. And we should talk about where these names come from. Isobutyl chloride, that hopefully is obvious, that name, because it's a chlorine on an isomer of butane. That's how that common name came about. And tert-butyl chloride. In particular, these two names, secondary butyl chloride and tert-butyl chloride, or tertiary butyl chloride, are referring to another aspect of alkyl groups, and that is the degree of how many carbons are attached. So we refer to this as the degree of alkyl substitution. So we designate different kinds of carbons depending on how many alkyl groups are attached. Okay, whether they're primary carbons, secondary carbons, tertiary carbons, or quaternary carbons. So if you take a look at this example, by the way, I'm using this symbol R. We use this commonly when we're just talking about chemistry to represent a generic term or a generic symbol for any alkyl group. So R could be anything, any carbon group. So when we refer to something that's a primary carbon, or sometimes we might say an alcohol attached to that would be a primary alcohol or a primary chloride. Would be a chlorine attached to that. What we're referring to is a carbon in which we have only one other carbon attached to it. Okay? So that's a primary carbon. Most often, that is, the rest of these are hydrogens. But like I said, a primary chloride would be one of those, maybe a chlorine. A secondary carbon is a carbon which is attached to two different alkyl groups. Okay? A tertiary carbon, obviously, attached to three different alkyl groups. And a quaternary carbon has 4 alkyl groups, no hydrogens or anything else attached to it. 4 carbon groups. Okay, so this terminology comes up a lot, particularly when we start to talk in chapter 4 and beyond on reactions of various functional groups. We'll talk about how the amount of substitution on a carbon really impacts the reactivity and the chemistry. And so I'll be using these terms a lot: primary, secondary, tertiary, and quaternary. Maybe not mostly quaternary, because there's no functional groups. So that is the origin of some of those common names. So if you take a look at those molecules that we were looking at before, these isomers of chlorobutane. Secondary butyl chloride now hopefully makes a little more sense, because if you take a look at that, it's butane with a chlorine attached, not to an end carbon, but to a carbon which has a secondary degree of alkyl substitution. Okay, this carbon the chlorine is attached to has 2 carbon groups attached. So to distinguish that in a common name from the other 3 other isomers of this molecule, commonly they just said that's the secondary butyl chloride, because it's the only isomer with chlorine on a secondary carbon. All right. And the tertiary butyl chloride, same thing. It's the only isomer of chlorobutane, which has chlorine attached to a carbon, which has a tertiary degree of alkyl substitution, 1, 2, 3 carbons attached to it. Make sense? Okay. If you take a look at the normal butyl chloride, it's not referred to as a primary chloride. It's not prime butyl chloride or anything like that. It's normal butyl. Although chlorine is attached to a primary carbon here. This carbon has only one other carbon attached to it. So that carbon is a primary carbon. The other isomer, the last isomer here, isobutyl chloride, that chlorine is also attached to a primary carbon. That's a primary carbon, chlorine is attached to it, so they can't really use primary chloride to refer to those and distinguish them, right? Because there are 2 of those isomers have them. Notice we have 3 primary carbons in this molecule, 1 tertiary carbon in this molecule. You should be able to look at a molecule and tell me how many carbons are primary, how many carbons are secondary, how many carbons are tertiary, etc. Okay, so you should be able to distinguish that. And that's quite simple, right? You just add up the number of carbons attached to it. It's really not that hard to do. Okay, so sometimes you'll see some of these smaller groups utilizing some of these common names as substituents. Here, for example, we just take the 3-carbon substituent, the propyl group. Okay, the IUPAC name would be propyl. The common name for that group would be N-propyl to distinguish it as the normal linear 3-carbon substituent, as opposed to being attached on the middle carbon, which is often referred to commonly as an isopropyl group. Okay. Notice, though, the IUPAC name is not isopropyl. It's very, very commonly used. I'll tell you, that one is used all the time. But the official IUPAC name for this substituent attached at the position I've indicated here onto a larger molecule is a 1-methyl-ethyl group. Okay? 1-methyl-ethyl. That's a little bit strange to think about. It's what we refer to as a complex substituent. Not just a simple linear chain off of a larger molecule, but a branched linear chain off of a molecule. So if you think about the naming system we have for alkanes and those branched alkanes, and if you have substituents off the side which are not part of the parent chain, but also have branching, you kind of think about that, naming that then in a subset of how we named our naming rules for the larger one, with a few differences. Okay? For complex substituents, how we name these is we start defining the name of the complex substituent at the point of attachment. It doesn't matter what else. Starting at the point of attachment, that's the first position, position 1 of the complex substituent. And from that point of attachment to the larger molecule, then you find the longest chain from there. So the longest chain from the point of attachment for this group is a 2-carbon chain, right? So that complex substituent has a, I'll call it a subparent molecule name of ethyl. Okay, so that's an ethyl group. But since it's complex, branching off, it's a branch off of a branch, branching off is a methyl group. That's why we refer to this complex name as an ethyl group with a methyl group at the 1 carbon of that substituent branching. So a 1-methyl-ethyl. And when you incorporate this into a larger molecule, this is all put in parentheses and then as the complex substituent. Okay, so let's look at an example. Let's take a look at this molecule. What is the longest carbon chain that is most branched in? It's 11 carbons, and it's the one I've drawn linear here. So that's the longest carbon chain, which is most branched. Notice this substituent here, though, has further branching, but if you started numbering here, you'd have fewer carbons. So that can't be the parent chain for this molecule. All right, so we have here a methyl group. Here we have an ethyl group. And here we have a complex substituent. Okay, so we have to come up with a name for that complex substituent. So how do we do that? Well, starting from the point of attachment, okay, number that. So that's carbon 1 from the point of attachment here. That's carbon 1, that's carbon 2, that's carbon 3. It's a 3-carbon group, so that's a what? 3 carbons would be a propyl from propane, since it's a substituent. It's a propyl group. And then branching off of that 3-carbon chain is a methyl. So the name for the complex substituent here should be what? It's a 2-methyl-propyl group. 2-methyl-propyl. So the 2 refers to its position on that side chain propane. On the propyl side chain, the methane is branched at the 2 position of that. Remember, you always start numbering from the point of attachment. So we have a 2-methyl-propyl group, we have a methyl group, and we have an ethyl group. All right. Now number this molecule, starting on this end, 1, 2, 3, 4, 5, 6, all the way up to 11. So a substituent on the 2-carbon, substituent on the 3-carbon, and substituent on the 6-carbon. All right. So alphabetically, that all gets put together. Ethyl, then methyl, then 2-methyl-propyl. All right, so that's how you would put it together. So if we write this all out, make sure I get this right here. We have 3-ethyl, 2-methyl. Is that big enough? Then the complex substituent. That complex substituent is on carbon 6, so we put a 6 dash, and then in parentheses, the name of the complex substituent, 2-methyl-propyl. Parentheses, and then the parent molecule is 11 carbons. Anyone remember what that is? Undecane, yeah, undecane. So that's the name for that molecule. But again, keep in mind when we have branching on side chains, referred to as a complex substituent, and it's kind of like a subset of our naming system from our normal naming system. Okay? If you follow those rules, it does work because everything is systematic and it works every time. The biggest area of confusion that I see students have about complex substituents is not remembering that they have to number the 1 position not on an end nearest a branch. When it's on a side chain, you always number from the point of attachment to a molecule. And don't start counting here, count there. That's the other area where people make a lot of mistakes. Okay? Are there any questions about naming of alkanes, branched alkanes, and complex substituents? Hearing none. Okay, the other aspect of alkanes is that they could be connected in rings. All right, so for example, the smallest possible ring you could have of an alkane would be a 3-carbon ring. And we name them as we would the alkane, the number of carbons that would be in the parent chain would be the number of carbons in the ring. But we just prefix that with the word cyclo. So the 3-carbon group that's connected in a ring, we would call cyclopropane. Okay? The 4-carbon ring, cyclobutane, 5-carbon ring, cyclopentane, and the 6-carbon ring, cyclohexane. Okay? Another thing I want to point out about ringed alkanes, you notice in order to make a ring, to connect, if you have a chain of carbons and then to connect the ends, we're missing something from the normal general formula for alkanes, right? What would we have to do to take propane and make it into a cyclopropane, for example? So what's the molecular formula for propane? CH3, CH2, CH3, right? That's propane. Well, if you wanted to connect these end carbons now, how do you make a bond? You have to remove something. You remove 1 hydrogen from each of those. So instead of having 8 hydrogens like we do with propane, cyclopropane only has 6 hydrogens. Okay? So a linear alkane or branched alkanes that have no rings, the general formula is CnH2n plus 2. That's for alkanes. Okay, the general formula for a cycloalkane is CnH2n. It's less those 2 hydrogens, otherwise you wouldn't be able to form that bond. Okay, the naming system, the naming rules that we had for naming linear and branched alkanes do follow through for cycloalkanes also. However, you have a few little differences. For example, if you take a look at cyclopentane here on the bottom with 1 methyl group, this is referred to as methyl cyclopentane. Since it's a ring, every position on the ring is identical. So if you have only 1 branch off of a ring, 1 substituent attached to a ring, there's no reason to put a number. There's no need to, because you always would define that as 1 anyway. So you don't need to write a number. That's why this is just called methyl cyclopentane. Only when you have more than 1 substituent, then you have to number the molecule so you know the relative positions of the substituents on the ring. So in that middle example, we have a molecule 1,3-dimethyl cyclohexane. And that's to distinguish it between other isomers where the methyl group could be in different positions. So when you name a ring, you always number in the direction that you start 1 at one of the substituents. You have to start at one of the substituents. Usually that's sort of alphabetical order, so whatever has the lowest alphabetical priority might be where you would start number 1. But the more important thing is you number in the direction that gives the lowest numbers overall, or the closest next substituent. If you were to take this molecule and number the other direction around the ring, 1, 2, 3, 4, 5, you wouldn't reach that other methyl group until you got to 5. Okay, so that would be wrong. You name it to give it the lowest numbers. So you go the direction around the ring towards the next closest branch. Or overall, if you have more than 2 groups, it gets a little more complicated. Then you have to number to give the lowest. So, for example, in this case, 3-ethyl 1,1-dimethyl cyclohexane. This is numbered this way because there are 2 substituents on one of the carbons and 1 substituent here. If I number here 1, 2, 3, if ethyl were the number 1 carbon and the methyls were the number 3, it would be 1-ethyl 3,3-dimethyl. So one way to do that is just, if you number it that way, add up all those numbers and see which comes out to be the highest sum. That would be the highest sum would be wrong. You want the lowest sum, the lowest possible numbers. Okay? Other than that, naming cycloalkanes is not a whole lot different. Same thing, you name the ring as the parent molecule, you identify the names of the substituents, you number it to give the lowest possible numbers, and then you put that name together, just like you would in alphabetical order, with the locats telling you the positions of what comes right after it, and the name parent. And don't forget the parent name cyclo. Okay? That's where I see people make the most mistakes in naming cycloalkanes. They forget to put the word cyclo. Or they'll name a linear molecule and call it a cyclo. So really be careful about that. Okay. Let's talk a little bit more about hydrocarbons. About 96%, I think, of the hydrocarbons that we have available to us come from crude oil, fossil fuels. That includes all the things we use for fuel, gasoline, natural gas, oils, and most of the chemicals that we use to make materials, to make polymers and plastics and to have solvents and things like that, most come from crude oil, okay? Which is a whole mixture of different kinds of hydrocarbons with different single bonds and double bonds. And at refineries, they can separate those based on boiling points. Okay, so you see here, for example, crude oil. They distill them into various fractions to separate lighter hydrocarbons from heavier hydrocarbons. But you can do a little more to that too. So if you want to get small chain hydrocarbons, propane and butane and pentanes, for example, larger ones can be broken apart thermally. They can just heat them under high pressure and you can crack them apart, basically, to break up large hydrocarbons into smaller ones. And there's also processes which can take some of those crude materials and reform them or convert them into more branched and ring compounds and aromatic compounds, usually under very high temperatures and high pressures. But you should recognize that most of what we have available today comes from the ground, and they are non-renewable resources. So if we burn up all of our hydrocarbons, we have nothing to make plastic out of anymore. And that would be a problem. Alkanes actually are nonpolar molecules, what we refer to as hydrophobic, or they hate water. Nonpolar molecules, and that makes sense because in order to have polarity in molecules, we need to have a large difference in electronegativity in the bonds, right? And then overall, we talked about molecular dipoles a couple of lectures ago. Overall, the sum of all of those dipoles has to be not zero. And the greater the difference in the electronic spreading through the molecule, the more polar it is. Well, hydrocarbons are just carbon and hydrogen. The electronegativities of carbon and hydrogen are not that much different. And so alkanes are generally nonpolar. Okay? However, even molecules which are nonpolar have some attractive forces between them, what we refer to as van der Waals attractions. Okay, and they arise simply because when you bring molecules close to each other, they can induce small dipoles within them and try to match them up. So there is still some electrostatic type of nonpolar, I won't say nonpolar, it is polar, electrostatic attractions that are temporary or transient that occur when molecules come close together. That's different than having a permanent dipole. They are induced transient dipoles. And those dipole matching and those attractive forces between nonpolar alkanes increase and are stronger when we have those more linearity to our chains rather than branching. And we see that affect the properties of molecules. So if you take a look at the alkanes here from methane to decane, you see that they have different boiling points. If you look at the boiling point. So one aspect to boiling point, of course, is the molecular weight of the molecule, and certainly that's a factor here in this increase in boiling points as you go larger. But keep in mind, a boiling point is referring to the point where a molecule goes from a liquid state to a gaseous state, right? The more attractive forces you have between molecules, the more energy it takes to go and separate them into a gaseous state. So some of this difference in boiling point is due to those attractive forces. As you get longer chains, you have more and more attractive forces between them, van der Waals attractions. So methane, I mean, if you take a look at just going from methane to ethane, you haven't changed, they're both very light hydrocarbons. Well, you've gone from a boiling point of minus 164 degrees Celsius to minus 89 degrees Celsius. That's a huge difference. Just adding one carbon. All right. The alkanes up to 4 carbons at room temperature are gases. Once you get to pentane and higher, those hydrocarbons are liquids. And if you get even larger, then the melting points even get above room temperature, and then they become like waxes and things like that, waxy substances, solids.
Was that just a typo that you would see for each time, like?
Did I? Yeah, that would be a typo, sorry.
Okay.
Yeah, that's a cut and paste error. I was going to fix that and I never got to it. Thank you for pointing that out. Well, this shows you the effect of those van der Waals attractions on boiling point. If you just look at the pentane and the isomers of pentane, they have very different boiling points. So normal pentane, 36 degrees. If you have the 2-methylbutane isomer, it's the same number of carbons and hydrogens, it's just branched now with one methyl group. Boiling point goes down to 28. And if you take this isomer to 2-dimethylpropane, now it's below room temperature boiling point. So it's a gas at room temperature. Although it has the same number and kinds of atoms. Okay, so that tells you right there that the more branching you have, the lower the boiling point. And that's due to decreasing the attractive forces between those nonpolar molecules. And that's a general phenomenon we see with alkanes. Well, what do? We know we can burn them. Since we use alkanes for energy, combustion or oxidation of alkanes is one of the main reactions that we have available to us for alkanes. This process, by the way, this is a process we discovered 50,000 years ago and learned how to harness, and it's the same chemical reaction we're using to power our world today, burning, combustion. It's kind of interesting. We haven't made much progress on that, have we? So another process is free radical coronation. Actually, once we get into chapter 4, we'll talk about more details of this process. Other than that, alkanes are relatively inert. They don't have real polar groups in them. The bonds are quite strong as bond strengths go. And to just break them apart takes a lot of energy or very highly reactive species to react with it. So this process, for example, relies on some way to generate chlorine reactive free radicals in order to react with alkanes. This oxidation works because it generates a lot of heat and it's a downhill reaction in terms of the energetics of the reaction. This process, though, of combustion is one that we can actually utilize to take a look at comparing molecules. So we define the amount of energy released when we burn an alkane as the heat of combustion. And that heat of combustion, if you look at the oxidation of methane here, CH4 plus 2 molecules of O2 give carbon dioxide and 2 molecules of water and lots of heat. Okay? And if you just compare the bond enthalpies from the starting materials and the products, this is how we calculate the overall heat of combustion or change in energy in this reaction. Combustion is a very exothermic process, that is, a lot of energy heat is released. And if you add up all the bond enthalpies of the starting materials and products and do this subtraction, you'll see that something like methane, you do combustion on methane, it releases about 213 kilocalories per mole of methane. It's quite a lot of energy. Obviously, if you have larger alkanes, you have more hydrocarbon in the molecule. It takes more oxygen to convert, you get more CO2, and you also get more energy out of that. There are more bonds you're breaking and making here. So if you take 2-methylbutane and you burn it, each mole of that will release 843 kilocalories. Okay. Obviously, if we compare methane to 2-methylbutane, we're talking about very different molecules with different numbers of atoms. So obviously, you would expect different amount of energy to come out of it, right? But what happens if we take a molecule that's simply a constitutional isomer? Has the same number of carbons and hydrogens, are just attached differently, and you burn it. Would you expect the energy to be different that's released? Yeah. Yes. Someone says yes. Why?
Depending on what kind of change you have on there, it might decrease the van der Waals forces and might allow for more oxygen to get in.
That's a good thought. The answer was you might decrease van der Waals attractions if you have more branches, and then oxygen can get in easier. Actually, this heat of combustion doesn't take into account the van der Waals attractions between molecules. It's looking per mole of the molecule itself and the bond enthalpies. But different isomers have different bond enthalpies. Primary carbon hydrogens have a different bond strength than a tertiary carbon-hydrogen bond. The degree of alkyl substitution matters. So if you compare, here's an example. How many carbons is this? 2, 3, 4, 5, 6, 7, 8. If you compare these isomers of the 8 carbon alkanes and look at the heat of combustion, the heat released on burning, what we see is that we get the most heat out from the linear alkane. And as we become more and more branched, we get less heat out. Okay? So in this way, we can directly compare the potential energy in those molecules. And what that tells us is something about the relative stability of those molecules. Since they're all burning, they produce the same amount of carbon dioxide and water. Okay, the only difference is the amount of heat coming out. That tells you how much energy that molecule had to begin with. Okay, so what this is telling us, this data right here tells us that the linear alkane is higher in energy than this highly branched alkane with the same number of carbons and hydrogens. And so if this is higher in energy than this one, what does that tell you about the stability? The branched one is more stable. Okay. Lower potential energy, more stable. Higher energy, less stable. Okay, so we can do that comparison on all kinds of molecules. As long as we're comparing specifically, if we measure heat of combustion, we have to be comparing molecules with the same molecular formula. We have to be comparing isomers. Okay, I want to talk a little bit about some of the definitions we have. So if you think about this process that we just talked about, methane, undergoing combustion with oxygen to produce heat and carbon dioxide and water. Well, let's just look at the carbon part of this. CH4 to CO2. Okay? And if we think about what we know and have learned about oxidation states of elements, and you think about adding that up, well, this looks like carbon has an oxidation state of -4. I mean, if we think about a proton as being plus, and then the C would be minus, right, in that bond, then we would think it must be C -4, right? So the oxidation state must be -4. And if we go to oxygen and think about oxygen as the more electronegative element, oxygen is 2- oxidation state. That means, I'm sorry. Yeah, oxygen is 2- here and 2- here. That means the carbon must be +4. So this is a change in oxidation of the carbon. All right, so in general chemistry, you learn about oxidation states of magnesium and lithium and sodium and things like that, because we can easily tell it gives up an electron and forms an ion. Lithium goes from 0 to the +1 oxidation state when it gives up that electron and becomes a lithium cation, right? Well, when we talk about organic molecules, it's not so straightforward as that, because when we go from this molecule to this molecule, we're not talking about ions. We're talking about molecules with covalent bonds. So this way of tracking electrons and electron ownership is a little more gray. There's a lot more in between in those oxidation states. But formally, we would think about that as C -4 and that as C +4. And then this process overall is an oxidation reaction. So you should be able to recognize organic molecules and whether they're more or less oxidized in a reaction. So we define the oxidation of carbon as, one way to think about that is increasing the number of bonds to oxygen. And that's what we've done here. We've gone from no bonds to oxygen. And now in the product we have 4 bonds to oxygen. But that's not true just for oxygen. It's true for any element that you've increased the number of bonds to an element which is more electronegative than carbon. And there are a lot of elements which are more electronegative than carbon. So that's probably a better way to think about it. You've increased the number of bonds to a more electronegative atom. Some like to think about that as decreasing the number of bonds to hydrogen. That's not necessarily that accurate either. The reverse process is a reduction. And so we would refer to a reduction of carbon as decreasing the number of bonds to a more electronegative atom. Usually that's increasing the number of CH bonds. Usually, not always, but usually. So if we take a look at some examples of what molecules might be at different oxidation states, this array of molecules here shows you molecules which have similar oxidation states to each other. So as we go from left to right, the carbon is becoming more and more oxidized. And you can see on this top row here, we have increased the number of bonds to oxygen from that carbon. Okay, but as I said, it doesn't have to be oxygen. So here, for example, those molecules have what we would refer to as the same oxidation state. Okay, and that's why the better definition is we've increased the number of bonds to a more electronegative atom. Because oxygen is more electronegative than carbon, chlorine is more electronegative than carbon. Carbon has 1 bond to a more electronegative atom. Those would be the same oxidation state. Okay, and so on. And you can have different configurations. So for example, these, right? Ch02 has the same oxidation state as carbonic acid, but it's a different molecule. But they both have 4 bonds to carbon. And that's comparable to carbon tetrachloride, which has 4 bonds to chlorine. Okay, I'm going to stop here. Have a good weekend, and we'll continue finishing up Chapter 2 on Monday. And we will probably, hopefully, start getting into Chapter 3. I should have the Chapter 3 slides up on the web by tomorrow.